702 and Cape Talk.
The Naked Scientist.
Who loves us so much. He is on holiday, but still will be imparting his knowledge with you and I. Hello, Chris. Are you well?
Yeah, I'm very well, thank you, Eusebius. How are you?
I'm extremely well. Can't complain. High spirits this morning. We had a question left over from last week, and I think we might be able to help the gentleman out. You did give us a caveat. It will depend on whether some of your other clever colleagues were available to answer. I'm going to replay it and to see whether we can help out the gentleman from last week who gave us some homework. Paul, welcome to the show. What is your question?
Yeah, hi, Chris. Hi, Steve. Okay, my question is this. When you take a clear float glass, to toughen it, it is put through a furnace. But prior to this process, if you need holes or you need notches made, you need to do it before it's fired. So anyway, recently I ordered a 8mm piece of shower glass, just one panel, and I requested 8mm holes in the panel to take a towel rail. I was told I can have 6mm or I can have 10mm, but I can't have 8mm because the diameter of the hole can't be the same size as the thickness of the glass, as it tends to shatter in the furnace. They don't know why, I don't know why, and I wonder whether Chris knows why.
What a lovely question, Chris. Okay, feels like deja vu. Chris?
Right, okay, I did my research because I'm not a materials scientist, and I had a feeling this had to do with something to do with the way in which glass has different parts of the material being in either compression or tension. So I called up a friend of mine called Howard Stone, who's at Cambridge University. He's a materials scientist. He works as part of his research with Rolls-Royce, helping to design alloys that go into jet engines, into the parts of jet engines that have to survive at extremes of temperature. So he's very familiar with how materials change and respond to changes in temperature, like putting glass in a furnace, and also how materials respond to stresses and strains. Now, he said, I don't know for sure because I don't know what the composition of the glass is, but what he points out is that when you take toughened glass, you end up with a situation where the center of the glass material is in tension, it's being pulled towards the edges, and the surface of the glass is in compression, it's squeezing in. When you put the hole through this, obviously you change the way in which forces are transmitted through the glass and how those areas of tension and areas of compression exchange that force or transmit that force through themselves. Therefore, you will fundamentally, if you put a hole of a certain size, affect in perhaps a critical way how that force is distributed through that patch of glass. It will also make a difference how far from the edge the hole is. So he thinks that it's likely in this case that there's a critical size here, that if you make the size of the hole a certain dimension, you will end up focusing force between those interfaces of the area of compression and the area of tension, and this will result in it breaking because there'll be uneven distribution of the forces in the glass. So I think this is probably where it's coming from, but without doing our own experiments, we wouldn't know for sure. But I think that's a very plausible answer. Why the size of the hole should be so critical, I'm not sure, and whether it's a red herring, that it's the same thickness of the glass or not. But without doing some experiments, we couldn't tell. But I think that sounds pretty plausible.
Okay, fascinating. Johan, good morning to you. What is your question for Chris?
Hi, good morning. My question is, do galaxies turn clockwise or anti-clockwise?
Chris, did you get that?
Yes, hello, Johan. The answer is they do both. And the reason galaxies turn at all is because they have angular momentum. The material that was formed in the early universe and then splurged out into space by the evolution of stars and prior galaxies, that material all had spin and embodied momentum. There is nothing to stop it turning. So if you add something that's turning to something else that's turning, the net resultant momentum or angular momentum will be the sum of the two. So if the material that got together to make a galaxy happens to en masse be on average spinning anti-clockwise, you'll get a galaxy that's turning anti-clockwise. So you would expect on the basis of chance to have equal numbers of clockwise and anti-clockwise rotating galaxies. And they're spinning because the material that made them was spinning in the first place. So our Milky Way galaxy The galaxy itself is a spiral. It is turning. There's a central black hole in the middle of the galaxy. There's dark matter throughout this galaxy that helps to hold everything together. And the planets and the stars that are in the galaxy are going around the galaxy. And there are planets in, say, our system, which are going around our star. They're all turning, and they're all turning because the material that made them was turning.
Okay, I'm going to take one from Twitter that's quite interesting here from Gustav. Gustav says, "Hi guys, great show. How does and I'm going to mangle this, Bossett River flow in both directions, west to east in the morning and vice versa in the afternoon? Apparently they say that it is the only river with that particular characteristic, and Professor Google tells me this is somewhere in eastern Croatia. Have you heard of that?"
I must admit I haven't heard of that river. I have been to Croatia, a very beautiful country. I'm not familiar with the river. The usual reason why rivers flow in two directions is because they're tidal. I don't know about that river. I don't know, therefore, if it has tides or if rivers it is connected to have tides, and so there may therefore be a consequent effect of that. I don't know for sure. But the most likely explanation would be that there is some kind of tidal influence over the water in the river. But we'd have to look it up. If we can have a few more details, or anyone else is more familiar with that river or knows about this story, please come back to us and see what we can do.
Let me pretend to be the naked scientist for 1 second with the help of Wikipedia. It says here, the river is known as meandering and extremely slow, Chris, and it has a very small inclination in its basin, less than 10 meters from somewhere until its mouth. It is known for a phenomenon of being the river that flows backwards, but it seems like that's an illusion. It's sometimes, with strong winds and being so slow, it appears as if the water is flowing backwards. Did I just sound clever?
You sounded fantastic because you answered the question as well. So another ding ding, we have solved another one.
Oh, there you have it, yeah. Sven, good morning to you.
Morning, how are you guys doing?
Extremely well, thank you. What question have you got for us? Can you stump Chris?
I don't know if I'll stump him, but I'm curious about a question that I've been thinking about.
Okay.
In the universe, right, we try to understand what the universe is made up of, and I want to understand what the difference is between dark matter and dark energy.
Okay.
Hello, Sven. Right, okay. When we look at the universe as we know it, and we look at the stuff that's out there, if we look at the matter, in other words, the material that we're made of, that the world around us is made of, and then we ask, well, what fraction of the universe is that? It's about 5%. So 5% of the universe is visible matter that we can measure. We know what that's made of. It's two subatomic particles, quarks, called down and up quarks, and some electrons, and they together make the protons, the neutrons, effectively the atoms that surround us. So that leaves a whopping 95% of the universe to account for. Now, about 80 years ago or so, people started looking at galaxies elsewhere in the universe, and they started asking, how fast do the stars go round? And they realized that the stars in those galaxies go round much faster than they ought to be able to unless there was something else which was gravitationally active hanging on to them. If that extra gravity in the galaxy weren't there, these stars, at the speed they're turning round in a big loop around the galaxy, should be being flung off in all directions. So there must be something in the galaxy holding on to them. They realized that that entity, which we don't know what this is, so we put the word dark in front of it to describe this entity, which is cold. We can't measure it really. It doesn't interact with things, or if it does, it interacts only very weakly, and it's gravitationally active. That we call dark matter. It makes up about 27% of the universe. Then that leaves behind the remaining, if we make the numbers easy, 5% matter, 25% dark matter. That means that we've got about 2/3 of the universe's mass still to account for. 75%, in fact, 3/4. So where does that all come from? Well, the rest of the universe's mass is in the form of dark energy. And this is bizarre, but when astronomers began to measure faraway objects in the universe, they realized that faraway objects are not staying the same distance from us. The light coming to us from them has stretched out. It's become redshifted. And light becomes stretched out like that when the space that it's had to pass through to get to us has got bigger. And that means that the universe is expanding And the further away we look, the further away things are going, and newer objects are expanding even faster in the universe than older objects did. So the universe isn't just expanding, it's expanding, and it's expanding faster as time goes on. So if something's getting bigger and it's getting bigger faster, something must be driving that expansion. And the energy to drive that expansion is this notional thing. Again, we don't know what it is, so we put the word dark in front of it, is dark energy. And this accounts for the vast majority of the universe. More than 3/4 of the universe that's out there is this funny entity, which in somehow is a property of space itself, that as the universe creates more space and grows, it gets more dark energy, which accelerates the process of expansion. So that's the difference between dark energy. Dark energy is driving the universe to expand and get bigger. Dark matter is a smaller fraction of the universe and is gravitationally active but weakly interacting with materials and things that we know about at the moment, but it holds everything together under gravity.
Fantastic. Jeannie, welcome to the show. Let your question out.
Good morning to you. I'd just like to ask the naked scientist, why is it that when older people speak, their voices quiver? What makes it quiver?
What a lovely question.
Thank you.
Thank you, Jeannie.
Thank you.
Hello, Jeannie. I think that not everything improves with age, unfortunately. And as we get older, we all become a bit saggier, a bit more wrinkly, and a bit shakier. And as you get older, you might, for instance, find that the muscles that you use to control your vocal cords weaken a bit. The nerve supply to them weakens a bit, and so they're not as easily controllable as they once were. And also, as you age, you might spend less time talking. I mean, a person who's in, say, Eusebius's job, their job is to talk all the time, and so their voice is getting a lot of exercise. A person who's a professional singer, their voice is getting a lot of exercise, and they have developed very good control of the breathing and the processes that we use to make sound. A person who doesn't spend a lot of time, especially as they get older, speaking and chatting and interacting socially with people, in the same way that if you don't go to the gym so often, your muscles do get a bit weaker because you don't need to have these enormous muscles. An older person's voice will become a bit thinner and reedier if they don't use it so much. So I think as a consequence of the aging process naturally making tissue a bit less elastic and springy. Secondly, the fact that if we use it a bit less, it doesn't retain its strength and vigor. And in fact, if you practice and you do more talking and more singing and that kind of thing, you probably will preserve those things into your old age better than someone who doesn't.
702 and Cape Talk.
The Naked Scientist.
Rami, good morning. Welcome to the show.
Yeah, good morning. How are you?
I'm well, thank you. What is your question?
My question is that who named our planet Earth, and why is it inconsistent with other planets that's been named after gods? And why is the moon not be referred with a name like all other celestial objects?
I don't know if I'm on a caffeine high, Chris, but I'm loving some of these questions today.
Yeah, I like the space theme.
Yeah.
I don't know why we called the Earth, but it certainly has been called that for a long time. I mean, the Romans called it terra, which is ground, probably because it was the ground we lived on. The moon isn't called the moon in ancient parlance. The moon had a range of different names. The Romans called it lunar for moon. So it hasn't always been called the moon. But who came up with those names in the first place? I don't know. I'd have to engage a historian for their help. But obviously, people have been obsessed with these things for a very long time because they really meant something to them. The moon was a very visible daily presence. Every day you'd see the moon rise and sink, apart from when you have a new moon, and it would do it regularly. So people spotted those patterns and they attributed enormous significance to it. And the ground beneath your feet decided whether you lived or died. And so I think probably for those reasons they gave them very highly, important names. People didn't know that the Earth wasn't the only place in the universe until relatively recently. I mean, you think in the 1600s, people began to realize there were other planets. Galileo invented the telescope and began to look into the heavens. People like Copernicus began to be daring enough to suggest that the Earth wasn't at the center of the universe. And at that point, people then began this whole business of spotting other celestial objects. They realized that stars included planets. The planets weren't just other stars; there were other bodies like the Earth out there. So we began to grow our knowledge, and out of that knowledge came a much better understanding of the universe. So probably part of it was that we were extremely proud of ourselves in the early days and attached enormous significance because we thought we were the centre of the universe, and then realised later that we're not.
Meenakshi, you've been holding on. Thank you for being patient. What is your question for us?
Hi, good morning. Good morning, Chris and Yubi. My question is this. Some time ago at the University of St. Andrews in Scotland, an experiment was carried out where they took a sphere and they rotated it at a very, very high speed. Now, that sphere disappeared. So I want to know from Chris, can he just tell us what exactly happened there and what was the explanation?
I'm not familiar with this experiment. So they took a sphere and rotated it at very high speed, and it vanished.
Yes, they rotated it at, I think, some of the fastest speeds that they've known on Earth. And then that sphere just disappeared.
Yeah, no, I'm not familiar with that experiment. If you can send me a reference to it, if you can just tweet at Naked Scientists a reference to the study that you're referring to, I can take a look into it, because it sounds a little bit fishy that we're not getting the whole story here. So if we can have a few more details,
please,
then
Meenakshi.
I'll certainly come back next week and tell you a bit more about it.
Okay, tweet us or just call us back or email us em@702.co.za, and then Chris will come back to that particular story. Tulasi Izwe, good morning to you.
Hello, Sipho. Good morning to you. Jason, my name. I need to find out. I became blind about a year ago, and I've had people. Someone talk about the bionic eye. I just wondered if the naked scientists would know anything about it. Or,
Yes. Good morning. I'm sorry to hear that you had a problem with your sight. The bionic eye refers to people developing devices that can take over the role of your eyes at the moment. What does the eye do? Well, the eye is a posh camera, which is interfaced with your nervous system. It's got at the back of the eye a structure called the retina, and in front of that retina is a focusing system, a bit like the one in your camera, which takes light and focuses it onto the retina. And the retina is this sheet of tissue which converts light waves into brain waves. Basically, it's layers of cells that are light sensitive. When light falls on them, it changes their electrical activity, and those changes in electrical activity are then sent down an optic nerve to the back of the brain, and they are compiled into the image that we see in front of us. It's bizarre, isn't it, to think that what you're seeing in front of you is being decoded on the back of your brain. But when the eye goes wrong, it can go wrong for many reasons, and it can be a problem with the front part of the eye, the focusing system. It can be a problem with the retina that decodes the light that comes in and turns it into nerve signals, or it can be a problem with the optic nerve getting the signal into the brain, or it can be a problem with the brain itself. So there's a range of different reasons why things go wrong, and a bionic eye will only be able to work for some of those problems. Usually there's something wrong with the eye itself or the retina, because what most of these systems rely on is that you put into the eye a light-sensitive device which sits on the retina that's no longer working, converts the light that's coming in and being focused onto it into electrical signals, which are then injected into the healthy optic nerves that can carry the signals to the brain. We're not yet at the stage where we can replace the optic nerve connections to the brain. If a person therefore has a healthy optic nerve and you can electrically stimulate the nerve cells that go into that optic nerve with one of these devices, you can begin to replace vision. And scientists at Oxford University and in Germany and many other places are doing pioneering experiments now and getting quite a lot of good success, where you can take people who have got blindness and can't see a thing, and you can get them being able to see in low resolution, admittedly, but see things again with these techniques. So it's coming along very fast, and it's very exciting.
Evander, talk to us.
Yes.
What's your question?
I would like to know, why is it that the right-handed people seem to be more intelligent than those
Really?
who use the left?
What do you base that on?
I want to encourage my baby to be using the right hand.
Evander, you sound to me like you might be left-handed. Chris?
Oh dear, Eusebius, careful. Don't tell my daughter either, because she's left-handed and she's pretty intelligent. So
is there a correlation?
Let's just demystify this one right away. There is no evidence that people who are left-handed are less intelligent than people who are right-handed. Okay. What they do have to do, in fact, is struggle with a right-handed dominated world.
Yes.
Because if you're left-handed, you'll make up fewer than 10% of the world population, and because the world is dominated by right-handers, then right-handers have made the world for right-handers. So pairs of scissors, tin openers, calculators, everything's for right-handers. So left-handers actually have to be much more adaptable in order to cope in that environment, which some people argue makes them even more intelligent and able to cope. Probably stretching the truth a bit far with that one, but it's certainly true that people who are left-handed do cope admirably well, and they certainly don't suffer from an intellectual decrement. It may well be, though, that they are better at sport. And the reason is that a right-hander spends the vast majority of their time competing against other right-handers. When they meet a left-hander on the tennis court or the cricket field, the left-hander will have spent the vast majority of their time competing against right-handers, but the right-handers won't have spent a lot of time competing against them, so the left-handers are an advantage. So as a result, it's not a bad thing to be left-handed, and you should certainly not try and encourage your children to go against their natural preference for their handedness, because you're not going to change that. I used to do my own little experiment with my daughter, because from a very young age I could tell she seemed to prefer using her left hand. So I would see what would happen if I would take the spoon out of her left hand and put it in her right hand, and then later on it was crayons and pens. And I would just do it subtly without telling her what I was doing and see what would happen. This is when she was about 1.5, 2.
Yes.
And very quickly she would just quickly transfer the device back to the other hand, and it was clear from a very early age that she was going to be a lefty. So let your kids use the hand that they prefer using. The days of banning people from using the wrong hand are over, thank goodness, and it was very, very bad for the people that happened to.
Actually, this is quite fascinating now that you tease it out as wonderfully as you always do, because there is a competitive advantage sometimes. I'm thinking immediately, I love watching cricket. I don't know if you do. And sometimes when you have a left-right-handed combination of batsmen at the crease, it can often immediately cause tactical woes for the other side because they've got to deal with an unorthodox situation.
Yes, exactly right. And we think that probably buildings have been manipulated because of right-handedness as well. If you think of castles and things that people used to build, defensive structures, and they had spiral staircases, the reason spiral staircases were probably invented, apart from efficiency of space, is that right-handers, because the spiral staircases all rotate to favour the right-handers, who could hide up the stairs and round the corner and then fight round the bend with the sword in their right hand. So any left-handed swordsman in those days were at a real disadvantage because their sword was in the wrong hand, wasn't it? trying to defend their castle. So you can see these sorts of impacts of left and right-handedness going back thousands of years.
Okay, Martin, I feel guilty. We have run out of time, but very quickly, give us your question. Go straight for it.
On social media, there was a strange post not so long ago. Later this month, I think on the 27th of August, there'll be what appears to be 2 moons in our skies. And they say this phenomenon has happened or happens once every 2,500 years or something like that. Okay. Is this true?
Okay, can we deal with that one quickly, Chris? Did you hear it clearly enough?
Yes, I did. I've not come across the idea that there are going to be multiple moons. So unless this is some funny optical illusion, I'm not aware of that story. But again, if anyone has a reference for me and they can send me this, it may be that it's got some sound science behind an optical illusion or something. I'll look into it, but I haven't come across any stories to suggest the moon is going to clone itself and have a twin.
Okay. Thank you, Chris. Have a wonderful weekend. We'll do this again next week, Friday.
Thank you, Seabus. Bye, everybody.